Yeah. So this is lecture 5. So you are actually giving a lecture on the hydrocarbon chapter. This is from chemistry 11. So I am Soumen from IIT Kanpur, Department of Chemistry. So as you know that in the lecture 4, whatever we have discussed, so we have discussed so far about the just for the 5-minute discussion or introduction, so that whatever I have discussed in the previous lecture, so that you can remember. So we have discussed like the isomerization, and in the hydrocarbon chapter, basically it depends on the hydrocarbons, the organic molecule which are actually the store of energy. So wherever you will go in this world, we need actually the energy, source of energy. Whether we are talking about any vehicle, whether any talking about any bikes, motor vehicle, all these things, everything, everywhere we need actually, or any the everyday living. So we always need kerosene or petrol or diesel or this kind of fuels molecule. So fuel. So for that purpose, we need actually. So these fuels are coming from the hydrocarbons. So now we have to know what are the hydrocarbons are in general exist in this nature, and how the synthesis or preparation of this hydrocarbon is going in industry scale or in laboratory scale. Laboratory scale we cannot synthesis the fuels, right? But in general, it is going the synthesis of this kind of hydrocarbon, the fuels are in the industry purpose, pharmaceutical, agrochemical, these kinds of industry. So in the last lecture we have discussed when we are moving from the when we are actually moving from the lower mass to the higher mass level, lower mass, let's say molecular mass of the methane and molecular mass of the ecosane. So that is the molecular mass is the actually C20, where the carbon is the number of carbon is the C20. And you know that the alkane general formula is what? CnH2n plus 2, right? This is the general formula of the alkane. Now you can see the moment we are going from methane to ecosane, there is a molecular mass is increasing. You can see 16. Now it is a 282. Now the moment the molecular mass is increasing, the boiling point also increasing, and at the same time, while melting point also increasing. Now the boiling point is what? What temperature we can say it is a boiling point? Suppose one molecule, boiling point in general it happens for the liquid compound, and the melting points happens for the solid compound. So let's say in which temperature the liquid compound gets evaporate or goes towards its vaporized state, then you can say this is the temperature. In which temperature it happens, the evaporation happens, or the liquid molecule goes to the vapor state, then only we can say this temperature is the boiling point. The melting point, the temperature, in which temperature, the temperature where the molecule get melted, right? Melted means suppose you have a solid compound. In this temperature, the solid compound get melted to the liquid compound. So that temperature, that the fixed temperature, that is the one fixed compound. So every compound has their fixed melting point. So there will be some range 5 to 10 degree Celsius or Kelvin, that's a degree Celsius. But that depends. The melting point and the boiling point is the actually constant. It cannot vary from the. It cannot vary whether you are measuring in Kanpur, whether you are measuring in somewhere else in outside of India. Melting point or boiling point will be same for every compound. Okay, and the constant. Now in this today's lecture, we will go to the some interesting thing that is called the substitution reaction. Now we know that the alkane molecule. Suppose we know any alkane molecule, C, D, C. Suppose 3 chain molecule, CH3, and then first we have to fill the octahedral, not octahedral, tetravalency of the carbon. Then we have to see this is also CH3. So now you have a suppose 3 molecule. Now activate this kind of alkane moiety is very difficult actually. Activating this kind of alkane moiety is very difficult. Okay. Now the question is how we can activate this one. So there are two ways. So either we need, so for the activation of this alkane means what? So we have to break this CH bond, right? So there are only the CC bond and CH bond. So we have to break either the CC bond or CH bond. But actually to break this kind of bond, it's much more harsh condition we need. Harsh condition means what? We need actually higher temperature. Higher temperature. Okay. Now let's say we need higher temperature. Sorry. We need either sorry. So we need actually high temperature, or we need actually sunlight, or H nu. This is called the H nu. So under this H nu photolytic condition, so what will happen? Suppose sun is there. Okay. So now this sun ray is coming, right? Sun ray is coming in this way. Now let's say you have some compound. This is, let's say, one organic compound. Okay. Let's say this is one organic compound. So this is actually called photon. Photon is coming. Now under this photolytic condition, what will happen? So this is called H nu. Now the ray is coming in this way. In this direction it is coming. Now you have a compound. This is the organic compound. Now what will happen? It will, suppose this organic compound bonded by one single bond. Now this bond will break. Okay. This bond will break homolytically. And it will give one, it will give two radical pieces. So there are two ways to cleavage of this kind of, let's say for an example, we go directly to the example. Suppose you have a CH bond. Okay. Now there are two ways to break this bond. So one is the heterolytic cleavage. One is heterolytic, where the one of which atom is the more electronegative, that will bear the negative charge. Heterolytic cleavage, that is C is, we know that between carbon and hydrogen, carbon is much more electronegative, so that is delta minus plus hydrogen delta plus. Now suppose what will happen? Now we have this is the heterolytic cleavage. Now we need a homolytic cleavage. So there are two ways. So one is the homolytic cleavage and another one is the heterolytic cleavage. Heterolytic cleavage is what? The heterolytic cleavage I already discussed. But in case of homolytic cleavage or homolysis, there will be. So you know that this is a this is a covalent bond, right? So there is actually one bond means two electrons. One bond means two electrons. Now this two electron is forming one bond between carbon and hydrogen. Now they want to, if you want to cleave this bond, then you have to either you have to give the high temperature, or else you need the photocatalytic condition, that is called the H nu, right? Under this condition only you can cleave this bond. Now suppose heterolytic cleavage I already discussed. So in the case of heterolytic cleavage, carbon will be delta minus and hydrogen will be delta plus. Now carbon has, now we want to go for the homolytic cleavage. We want to see how the homolytic cleavage can happen. Now, so in this condition, what will happen? This bond will break, means there are two electrons. Now these two electrons will share by each other, each one electron. Now suppose carbon will take one electron and hydrogen will take another one electron. In this way, they will share the electrons. Now this is called the homolytic cleavage, where the electrons are shared between two atoms. But here, who is in heterolytic cleavage? What happens? Who is the more electronegative? It will take the electron density towards itself, so that the less electronegative atom contains positive, bearing the positive charge. Now, so let me erase this part. Then I'll go to what are the example as given in your textbook. Okay, this is the general formula, a general mechanism for how the homolytic cleavage and the heterolytic cleavage can happen, or how to activate your alkane substrate, or alkane means hydrocarbons. Now we'll go for the halogenation reaction. So in your textbook, they are actually discuss about the halogenation. Now halogenation means what? In periodic table, we know that how many halogen atoms are present. We know that fluorine, first is the fluorine, which is the most electronegative atoms. Now the fluorine, chlorine, bromine, iodine, fluorine, chlorine, bromine and iodine. So these five atoms is already present in a periodic table. Now we are not discussing about the other halogen atom. We are only discussing about the chlorination. That is the halogenation, right? So we first took the CH4 and Cl. So in this slide, I will not go for the entire mechanism for this part. So I have the all the mechanism for this thing. But first I will whatever in your textbook it is there, I will say that is. So under photolytic condition, you can see H nu. What will happen? So CH4. Suppose we have a methane molecule. Methane is a gas. You know that. So bracket we have to write that methane is a gas. Now chlorine. Chlorine also we have a gas molecule. We know that chlorine also gas. Now under photolytic condition, what is happening? Under photolytic condition, what we are getting? Actually, we are getting the CH3Cl plus HCl. Now this CH3Cl, what will happen? This is called chloromethane. CH3Cl is the called chloromethane. Now this CH3Cl will under photolytic condition, what will happen? Under photolytic condition, it will give the CH2Cl2 plus HCl. Dichloromethane. This is called dichloromethane. This is called dichloromethane or DCM. Okay. Dichloromethane or short name is the DEM. Okay. Now you have a CH2Cl2, right? You have a CH2Cl2. Now under this photolytic condition, what will happen? It will form the CHCl3. CHCl3 plus HCl. Okay. Now you can see the trichloromethane. This is called trichloromethane. This is actually trichloromethane. This is called trichloromethane. Okay. Now this CHCl3 plus Cl2 under H new condition, under photolytic condition, what it will give? It will give the CCl4. CCl4 plus HCl. Okay. So what it is actually happening? So in the presence of CHCl3, CH3Cl, so what it is forming? Actually, it is forming the CH2Cl2 dot plus HCl. Now this CH2Cl, so what is happening? So you have this one. So under photolytic condition, it will form CH2 dot Cl. Now you have this chlorine, another atom is there. Now this chlorine atom it will go the photolytic condition Cl dot plus Cl dot. Okay. Now this Cl dot and CH2 dot Cl, what it will form? It will combine together and one hydrogen extraction will happen here. Then you will get the CH2Cl2. Understand? CH2Cl2 plus HCl. Now suppose you have a CH2Cl2. Now you are actually under photolytic condition same way. Now CH2Cl2, another proton will get abstracted by and another proton will get deprotonated and it will form the CH dot Cl2 plus H dot under photolytic condition, and you have Cl dot plus Cl dot. Now you can see, so one Cl dot will react each other and H dot will react here, HCl. So what it will generate? HCl plus CHCl3. Now you have a CHCl3. Okay. Now you have a CHCl3. Okay. Now suppose you have a CHCl3. Then CHCl3, what will happen? CHCl3 under photolytic condition, what it will give? Under H new condition, what it will give? It will give the CCl3 dot. CCl3 dot. Okay. Plus H dot. And also same way you have a Cl2. Then under photolytic condition, what it will give? Cl dot plus Cl dot. Now it will react here and Cl dot will react here. Then what you are getting? CCl4 plus HCl. And this is called the tetrachloromethane. You can see. So in the textbook it is also written there. Although they have not written the proper way, but I have explained everything here. Still, if you have any doubt, you can ask me. But here they are also saying the also alkanes can be not only by the halogenation. So our main motive is the to substitution reaction has to do with the alkane moiety. Now not only the halogenation, we can also do a lot of things like not only halogenation, nitro group, sulfonic acid group. These are all things we can do here. Okay. So now the question is, we'll here only discuss about the halogenation moiety, not the other. Now suppose in the previous slide we have discussed only the CH4. This is the lowest alkane of the hydrocarbon moiety, hydrocarbon family. Now we are going from CH4 to another higher carbon alkane, that is CH3, CH3 and CH3 alkane. Now this alkane CH3, 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 CH3 plus Cl2, and under photolytic condition, what it will form? CH3, CH2, Cl plus ACl. How it will forming? So it is forming in this way. So under photolytic condition, what it will generate? It will generate CH3, CH2 dot plus H dot. And this Cl2 under photolytic condition, what it will form? Cl dot plus Cl dot. Okay, now this H dot and Cl dot will react together, and this Cl dot will react here. Then what you are getting? The CH3, CH2, Cl plus ACl. Now here the most important question is, they are asking the rate of halogenation with alkanes. It depends on the much more weaker. If you have the weaker bond, then it will be faster. So let's say when we are discussing about, we know that we have the fluorine molecule, bromine molecule, and iodine molecule, right? So we have four, this halogen moiety. Now we know that though this fluorination is too much violent and too not controllable. But chlorination, we can see the chlorination can happen easily, but chlorination is much faster compared to the bromination, and iodination is too weak and too slow and reversible reaction. So for that purpose, if you want to do iodination of an alkane moiety, then actually we need the higher oxidizing agent. Okay, we need actually higher oxidizing agent. And another way also we can say, so the moment it will form the halogenous substitution reaction of the alkane moiety, you can see, so there is a formation of the CCl, CBr, and CI. Now the question is, where the bond formation energy means the overlapping. Bond formation means what? The overlapping between the carbon p orbital and the chlorine orbital, right? So suppose you have a 2p, carbon is 2p, now 2p, so in three cases 2p is constant. Now when you are going from the fluorine to chlorine to, so from chlorine fluorine is 2p, right? Chlorine is 3p, this is 4p, and this is 5p, iodine is 5p. Now you can just imagine, so here one smaller, suppose 2p is orbital is this one. Okay, now 2p and 2p, so there will be equal overlap, right? 2p size mapping means good overlap. Only it happens, bond forming only it happens if the overlapping zone is good. When the overlapping is good, then only the bond formation happens. So when we are moving from 2p to 3p to 4p to 5p, there is a tremendous size increasing of the p orbital. Now you just think, so you have a 2p constant and the size of the other orbital is also increasing, then there will be not such matching. People say sometimes that matching also matters for the orbital overlapping. So that's why when you are going from the 2p to 3p to 4p to 5p, there is the overlapping zone will be less. So that's why the formation of CI is much more weaker. Not much more means they don't want to form the CI bonds. CI bond formation is very much you need actually harsh condition. So that's why we need the oxidizing agent like HNI3 HNO3 or HIO3, pyridic acid or nitric acid. Okay, so these are all things we have to think here. So now, and also one more important thing is that as we are discussing about the radical chemistry, then we have to think about actually the how the radical. So after let's say alkane moiety, so it depends on the radical stability. So if your radical is much more faster, so if your radical is stable is 3 degree, 2 degree, and then 1 degree. Okay, so if your radical formation is 3 degree radical is forming, so that means it is a more stable radical compared to 1 degree radical. Okay, now this is a 2 degree, this is 3 degree, 2 degree, and 1 degree. So this is how it works. So if you have the alkane in the more stable radical, then it is very easy to correlate here. Okay, so this is the, let's say you have a 3 degree radical. So 3 degree radical, one example is the CME3. We already also discussed in the last chapter CME3. CME3 dot is the 3 degree radical. This is a 3 degree radical. It's much more stable compared to CH and Me2. CH Me2. Me2 dot. Now CH Me2 dot to CH2Me. So this is a hydrogen, and this is a hydrogen, and this is a methyl. So this is a 2 degree, this is 1 degree. Okay, this is the stability, and also I have given some examples so that you can also correlate. Now we'll go to the formation of the, as we are saying that the formation of the substitution of the iodination is much more difficult because of the reversibility. So this is actually called reversible signature. So whenever you see this kind of thing, so this is called reversible. Why? So this means this reaction can go either this direction, or again this reaction can go either this direction. So that's why reversible. So that's why this signature indicates your reaction is reversible. Reversible. As in your textbook they are saying that this iodination reaction is reversible. So that's why they have given this kind of signature, this kind of arrow. But where it is irreversible, so then that time only single arrow. Now you can see, so when you have a methane molecule or I2 molecule, iodine molecule, so what you are getting CH3I. You are not going to the CI4. Where in the chlorination product, you are actually end up in getting CCl4. But also same way we can also end up in getting CI4, right? But here it is not possible because of the reversibility. The moment it forms this CH3I and HI, again it come back to the starting material, the CH4 and I2. Now the moment you add this one, HiO3 and 5HI, what will happen? So you have to completely consume in your reaction mixture HI. So for that purpose, we use this oxidizing agent, either HiO3, that is called pyridic acid, HiO3 or HNO3, pyridic acid plus 5HI. The moment you add the 5HI, it will form the 3I2. How? Now you have to match the number of iodine, number of hydrogen, and number of oxygen. Okay, see, you can see, so HiO3, you have the HiO3. So hydrogen is 1 and 5 hydrogen is here. So total 6 hydrogen. So suppose let's say total 6 hydrogen, and iodine is 1 and 5 iodine. So total 6 iodine. And now this is also 6 iodine. And plus, so you have in the left side how many hydrogen is present? 6 hydrogen. So here also 6 hydrogen. And plus here it is a 3 oxygen. So you can see 3 oxygen is here. Here also 3 oxygen. Now it is matching here. Now the question comes, as I already told you in the beginning of this lecture, that this reaction mechanism, this radical pathway actually go in 3-step way. How? So one is the initiation, second one is the initiation, one is the it first go for the initiation step, initiation, then it goes to the second one is the propagation. Second one is the propagation. Second one is the propagation, and the third one is the termination. Third one is the termination. Third one is the termination reaction. Now, so first we'll discuss about the what is initiation reaction. What is initiation reaction? So what is initiation reaction? Let's say for example we take the first example, that is the Cl2. Now the reaction is initiated by homolysis of the chlorine molecule in the presence of light or heat. The Cl bond is weaker than the carbon and CH bond, and hence it is easy to break the chlorine molecule. So they are saying, so if you have the CH4 molecule, so or else CH3 molecule, and you have a Cl2 molecule. So there is a possibility. One is so what are the bonds can be broken? So one is the CH, and another one is the CC, and the third one is the Cl bond here, and Cl bond. Cl bond. Now this is a Cl bond. Now you have let's say I need actually Cl dot radical. So first they are saying the bond breaking of this Cl bond is much more easier compared to the CH bond break or CC bond break. So the moment it will form, so if in your reaction mixture means what? Suppose in a pot where you are keeping the reaction, so you have a RB, round bottom plus, or any slang team, RB means how it's look like. So this is a RB, let's say. This is a RB. So here you have a reactant, substrate, all this substrate you have added here. Now this is called the reaction mixture. So in your reaction mixture, what will happen? Suppose you have any alkane moiety and Cl2 molecule, and you are adding the photolite, and you are now subjecting this substrate under photolytic condition. So under this photolytic condition, what will happen? So this bond will break easily. Now what it will form? Cl dot and another Cl dot. Now the moment it will form the Cl dot, then this is the main initiation part. So the initiation part, only the chlorine radical it will form. Then the moment chlorine radical it will form, it will go to the propagation step. So what is the propagation step? So in the propagation step, the chlorine free radical, whatever you are generating in your reaction mixture, it will go and attack to the methane molecule, and it will abstract one proton from the CH4 molecule. Then what it will form? So in the propagation step, so you have a Cl dot, you have the CH4, and under photolytic condition, what it will form? So it will abstract a proton from here. Now it will form the CH3 dot molecule plus HCl. Now you have a CH3 dot molecule. Again you have another chlorine molecule. Cl2 molecule is there. So now what it will have formed? So CH3 dot you have. Suppose CH3 dot. You have CH3 dot, and now you have a chlorine molecule Cl and Cl. Now what it will under photolytic condition? What it will form? Under photolytic condition, it will form the CH3 Cl plus Cl dot. Cl dot. Now this Cl dot, again it will go and react with this thing, this CH3Cl. Then what it will form? It will form the HCl plus CH2Cl dot radical. So this is called CH2Cl dot radical. Now again, so you have now this free radical. Now this free radical, it will react with Cl2. So you have CH2Cl plus Cl2. Now under this photolytic condition, what it will form? It will form the CHCl2 plus. Okay, I think we have some mistakes here. So CHCl2 plus HCl. Okay, so what it will form? It will form actually Cl2 and again Cl dot. Okay, so it will form the actually CH2. It will form the 1 minute. Yeah. So it will form this dot. It will now this chlorine radical it will form. So two chlorine radicals. So one chlorine radical will go and attack here. So what it will form? It will form the CH2Cl2. Now it is a neutral molecule. CH2Cl2 plus Cl dot. Now this Cl dot, what it will do? This Cl dot, you have this one and you have Cl dot. So what it will form? It will form actually the CaCl2 dot. Okay. Let me go to the next slide. Now, next slide we don't have space. So here let me erase this part. So let's say now we have a CH2Cl2 plus Cl dot. Okay. So what it will form? It will form the CH2Cl2 dot plus Cl dot. No, sorry. CCl2 dot. Okay. CCl2 dot. So you have this one now and HCl. How? So let's say you have a Cl dot. Okay. So here one proton is taking up this chlorine radical. It will take the one proton from CH2Cl2. Now you have a CaCl2 dot and one extra hydrogen external by Cl dot and it will form the HCl. So you have now this one. Now again you have in your reaction mixture CHCl2 plus Cl2. Now what it will form? It will form the CCl CHCl3 plus Cl dot. Okay. CHCl3 plus Cl dot. Now this Cl dot, you have this Cl dot and this one you have now, right? Now this Cl dot will here, it will abstract here. What it will form? CCl3 dot plus HCl. So these are all happening in the propagation step only. So you have CCl3 dot and HCl. Now this CCl3 dot, okay. Now suppose you have a CCl3 dot. In your reaction mixture, another chlorine molecule will come and will react here. It will give the CCl4 plus Cl dot. So actually, this is one of the catalytic cycle, right? Catalytic cycle means if we start from here, I have to generate this radical only because this is the main radical. It is forming, right? It is the actually initiator to forward this reaction. So anyhow, in your one of the moment you form this one, this is your suppose product. So then you have to again initiate, again reform this Cl dot, so that your reaction goes in catalytic way. So that means in your once your product formation happens, again your starting material get back, and again it will go until unless your all the CH4 get consumed. So we want to actually consume totally CH4 to CHCl4. So for that purpose, we need one catalytic cycle, right? So for that, we need actually initiate a Cl dot. So anyhow, in your reaction, after the moment you get the product, you have to again generate the Cl dot radical. So this is how the propagation step works. Now I will go to the termination step. Sorry, just 1 minute. Okay, so now what will happen in the whatever I said, they are also saying in this way. So we don't need to discuss this part also here because I already discussed here. So then they are also saying that your CH3 dot and the ClCl, it will from the CH3Cl, then you will end up in getting methyl chloride. This is called the methyl chloride. We are also getting the CH2Cl. This is a DCM. We are also getting. We already know. Now the main point is the termination step. So what is the termination step? Termination step means the reaction stops after some time due to the conduction of the reactant. So termination means what? Termination itself, it is saying that your reaction is got terminated. That means your reaction is not going forward. So that means somehow my reaction is prohibited by someone. How? Either my what happens? Either my the fully consumption of the starting material happens, or my any side product is happening, means the compared to my main product, my side product is forming the more amount. So that's why maybe my termination step is the much more. That's why I'm not getting my expected product. So the moment you will get this one, Cl dot and Cl dot, so you are actually generating the Cl2. So Cl and Cl. Now you have we know that in the reaction medium here it is forming Cl dot radical and Cl2. You have also generating CH3 radical. CH3 radical also we are generating from where? CH4. From methane only we are generating CH3. So we know that only one CH3, the moment it will form the CH3, so it can go for the homocoupling reaction, right? CH3 dot and CH3 dot. Now the moment when they will couple each other, then what it will form? It will form the CH3 and CH3. CH3 and CH3. Now this CH3 dot and Cl dot, CH3 dot plus Cl dot, it will form the CH3Cl. It will form the, so you have also another chance. So there is a CH3 dot and Cl dot, it will also form the CH3Cl and also CH3 and CH4. So these are all the side product can happen. And also one of the important question is your need exam or your final exam, they can ask that from the methane substitution reaction when you are doing, how you can get the ethane molecule. This is called ethane. So this is CH4 is the methane. This is called methane, right? CH4 is the methane molecule, and this CH3 is the ethane molecule. This is called ethane. This is the ethane molecule. Okay. Now let's say methane and ethane you have. Now though in CH3Cl, the one of the products is formed, but free radicals are consumed and the chain is terminated. The above mechanism helps us to understand the reason for the formation of ethane as a byproduct during the fluoridation of the methane molecule. Okay, now so this is the main reason as a byproduct is the ethane molecule. Now we'll go to the substitution. These are all the substitution reactions. Substitution reaction means what? You are substituting one of the atom by the other atom. So one of the hydrogen atom is substituted by the chlorine atom or any halogenated atom. Halogen may be the chlorine, bromine. Okay. Now we are discussing about the combustion reaction. So what is combustion reaction? We know that the alkanes are actually the store of energy storage as a used for energy storage. So alkanes mean the hydrocarbon chain. So the hydrocarbon chain means the carbon. The alkanes are mainly made by the carbon and hydrogen molecule. So alkanes, after heating in the presence of air or oxygen, are completely oxidized to the carbon dioxide and water with the evolution of the large amount of heat. So this is the CH4 plus O2. So we know that both are gas, right? Methane also gas, oxygen also gas, and the carbon dioxide and water. Water is a liquid, so that's why in the bracket it is written as a liquid. This is the liquid and carbon dioxide is the gas. So this is the ACM 890 kilojoule per mole. So this is the C4H10 13 2 oxygen and 4 carbon dioxide plus 5 H2O. So this is the liquid. So this is a liquid molecule. Now the general combustion of this reaction is so people can ask you the general combustion equation for any alkane is what? So we know that the alkane moiety general formula is the CN and H2N plus 2. So this is the general formula of the CN H2N plus 2. General formula for the this alkane moiety is the CN H2N plus 2. This is the 3N plus 1 divided by 2 and oxygen. This is a N carbon dioxide plus N plus 1 water. Okay. So how many water molecules? So that means what? So if you have a N equals to so if you start from the methane molecule, how many water molecule will generate? It will generate actually 2 molecule of water, and carbon dioxide also, lot of carbon dioxide. So one carbon dioxide is also generating from the one methane molecule. So now you can imagine, so the moment you have a more and more carbon chain, there will be more number of generating of the carbon dioxide, and the number of heat, the amount of heat it is generating is too much. So that's why you can say the alkanes are the source of actually energy. And CH4, C4H10 plus 13 by 2 O2 4O2. So you can see the amount of heat is generating. The moment you're going from the moment. So now let's say suppose you have a n equals to, so what will be the equation for the n equals to 3? So 4, when n equals to 4, they have written one of the equation here. So I'll write, so let's say suppose n equals to 3. Suppose you have a n equals to 3. Now let me write the structure of the write the equation for this one. So n equals to 3 means C4, sorry, C3 and H8 plus 3 equals to 3, then 3 into 3, 9 plus 1, 10. So that means 5. 5 O2 and n equals to how much carbon dioxide? So total 3 carbon dioxide, bracket a gas molecule and plus what it is generating. So 3 plus 1 means 4 water molecule. Water is the liquid. So in the bracket you can write as a liquid. Okay, so now we are generating this one. So, but in one water molecule, they are getting 890. So the moment it is going to the 4, so 8 into 4. So that means there is some other equation how we can get the amount of heat, how it is generating. So this maybe I will come with some of the problem answer session, the last lecture. I will go how to calculate the heat of this energy. Okay, so then due to the evolution of the large amount of heat during the combustion of this reaction, the combustion of alkanes are used as a fuels, as I already told you. Now they are saying they're incomplete conversion. So during incomplete conversion of alkanes with insufficient amount of air or dioxide, carbon black is also formed. So carbon black means what? Carbon and solid. Carbon black means the solid. So you are actually dealing with gas. Methane is the gas, but incomplete combustion, when it will happen, you will generate the carbon solid compound. So this is called the carbon black, is formed, which is used in the manufacture of ink. So where it is used in the manufacture of ink, printer ink or black pigment as a filters. Now the control oxidation. So now the alkanes on heating with regulated supply of dioxygen. Regulated supply of dioxygen means suppose oxygen 1 atmosphere. So there is a cylinder from where, so suppose there is a meter. So this meter will tell you, so this meter 1, 2, 3, 4, like that the number is given, and this meter is connected to a cylinder. Okay, so from there, so let's say this is the oxygen cylinder. So this oxygen cylinder is connected to a meter. This is called meter. Okay. Now this another valve is there where you can take the oxygen from this valve. These valves. So from here you are taking the oxygen here. Now you want to take only the 1 atmosphere of the oxygen. So the moment you will take the 1 atmosphere of the oxygen, you can actually regulate this compound, regulate this reaction, and you have the closed vessel. Closed vessel where you are doing this reaction in a closed vessel, there will be nothing can be go out. So when you are doing is so although they are not given the what amount of oxygen atmosphere pressure they are doing this reaction, but it depends how much pressure you will give. So if you start from the methane under oxygen, what it will form? Methanol, CH3OH. So this will be CH3, not ammonia. So this will be CH3OH. Then so that where we need actually what kind of oxidation catalyst? Copper mediated catalyst. Also they are given the 100 atmosphere oxygen bar pressure. 100 atmosphere oxygen bar pressure is too much. Okay, so in this harsh condition, this is called actually harsh condition. You can see the temperature 523 Kelvin and 100 atmosphere oxygen pressure. By this way only it is forming the methanol, and now you have a CH4 molecule. Okay, you have a CH4 molecule, you have a oxygen, and under this photolytic condition, molybdenum dioxide, molybdenum trioxide, it is forming the formaldehyde. It is forming formaldehyde. This is called actually formaldehyde, or in other way around, you can say this is called formaldehyde, or in other around, you can say this is a methanol. Methanol. Okay. So then what it will form? So you are suppose they have given three example. One is the methane molecule. One is the methane molecule with different catalyst where they are getting non-methanol. They are getting methanol formaldehyde. And when you are taking the ethane molecule under oxygen pressure and manganese acetate, MnOAc whole 3. Actually, it will be whole 3. Manganese OAc whole 3. Then what it will form? Manganese OAc whole 3. It will form in under heat condition. It will form the acetic acid, CH3 COO8, CH3 CH3 COO8 plus ethanoic acid. Okay, so this is called the ethanoic acid and water. Okay, so now, so here I am closing these slides today. So maybe the next class we'll discuss about what are the things left. That I will try to finish it quickly. Maybe tomorrow, if I get one chance, I will finish it. Not finish it means I will take the class, and again the whatever 3 class I have taken, I will finish the question answer section of this part. Okay, thank you.